Okay. So last time we looked at how to design the MIPS processor, and actually we are completing the design of this MIPS processor. As I mentioned, this one should be finished on next Monday. So you have to submit your design through the portal site. Okay. So when we are looking at this one, if we are changing the clocking, then you can see that every clock is changing, then new value is updated into the register, right? So that means it is executing the processor. So it is updating the PC value, from count value, and also after the result of computation is coming to the processor register and is waiting until the next cycle is changing. Okay. So let me summarize our design. So if we are summarizing the MIPS processor, then in the abstract way, the first component is instruction fetch, right? So this is fetching the instruction from the instruction memory. And also this one is increasing the pro and counter value. And then what we are doing is we are analyzing the instruction, okay? And so instruction decode. And during the instruction decode, we are also reading the register value. And after instruction decode, the result from the register is coming out, and we are applying the some ALU operation. So like this is execution stage, which is computing the ALU, or it is computing the address. And then what we are doing is there will be some memory. It's depending on the instruction type. So if this is a load store instruction case, then we have to update or read data from the memory. If this is just the ALU operation, all-time instruction case, the memory part will not be executed. And then the last one is write back. So we are updating the register value. Okay. So component-wise, there is no write back because the output of execution. So if we are drawing the physical component, it looks like this. Physical component case, we are doing the instruction decode, and then there is a register, and there is ALU. And there is memory. And the output of ALU and memory are selected, and the result is updated to the register. Okay, so this is kind of hardware structure. And the last part here, memory, where register value is updated, that is called write back. Okay, so we can design this one. So let's think about some instruction like all-time instruction. Then which hardware is actually used? So instruction fetch, we always have to execute, right? After we are executing, we can start to analyzing everything. So instruction fetch we need, and instruction decode we need, because all-time instruction case, we have to read register value, and EX execution, that is also required, right? ALU operation is required. And then memory, we don't need, right? Alt type is not access the data memory. Okay. What about the write back? This is required. After the result is coming out, we have to update the register value. Write back is required. Add I instruction. Instruction fetch is required. Instruction decode, execution, write back. Okay. What about load instruction? Instruction fetch, instruction decodes, execution to compute address, and we also have to access the memory to read data in the memory. And finally, we have to update register value. What was the store instruction? Instruction fetch, that is every instruction is required. Instruction code, that's required. Execution. Memory, we have to update the memory. What are the write back? Store case, we don't need to update the register value, right? Register value is written to the memory. So that's it. Branch equal insertion fetch, insertion decode. And in our implementation, during the execution, we are extracting out the zero value, right? So after execution, we know that whether two register values are equal or not. So after execution, we know that. That's all. Jump, insertion fetch. Actually, we need the instruction decode, but we don't need the register read, right? So maybe insertion decode, maybe insertion fetch, or like this. Okay, so if you are looking at the instructions, then each instruction takes a different execution time. Which one requires the longest path? Yeah, definitely load instruction, right? Load instruction case is a fetch, decode, execution, memory, write back. Everything should be executed, right? Which one is the shortest one? Maybe this one, right? Short. And this is longest. So when we are executing instruction, what we have to do? We have to changing the clock, right? So clock should be changing. When clock is toggled, then one instruction is executed. Okay. So if there are many instructions, so let's say to execute all type, it takes like 10 nanosecond, and this one takes also 10 nanosecond. Load instruction 20 nanosecond. Store instruction like 15 nanosecond. Branch equal like 8 nanosecond. Jump instruction 7 nanosecond. So if let's assume that each instruction has different execution time. Okay. So among this one, what is clock cycle? What's the possible clock cycle? So there are 10 nano, 10 nano, 20 nanosecond, 50 nanosecond, 8 nanosecond, 7 nanosecond. So which one do we have to choose for the clock cycle? If we are choosing the short clock cycle, for instance, 7 nanosecond, then what is happening? Load value is not coming out, right? So load case, it takes long path. So load case, this output of memory should be coming out, but because of that length of circuit, that is not prepared yet, but we are changing the clock. Then incorrect value is stored into the register, right? So then clock cycle should be longest one. Longest clock cycle, longest instruction. Right? So it should be 20 nanosecond. Okay, so either we can think about two things. One is fixed clock cycle. So fixed clock cycle means that every instruction, the clock cycle is just fixed. Or we can varying clock cycle. So clock cycle is depending on the instruction. But actually the changing of the clock cycle is difficult, so much difficult to be implemented. So this is not going to be used. Okay, so changing the clock cycle is not easy at runtime. It takes a lot of times actually. Okay, so for instance, if it is also possible. So for instance, 2 gigahertz machine can be changed to 1 gigahertz. That is possible in the modern processors, but to change the clock, it takes a lot of cycles. for this one, it's like it takes more than 1,000 cycles. So, which means that every cycle you cannot change the clock cycle. Okay, clock duration is not going to be possible. So, you are just assuming that clock cycles are fixed. So, in that case, clock cycle duration should be longest one. Okay, like 20 nanoseconds. So that's the problem. So we have performance issue if we are using the our current design, because longest delay, longest instruction is determining the clock period. Okay, so like a load instruction that is reading instruction memory, register, ALU, and memory, and write back. So we have to accumulate all the execution time to determine the clock cycle. So like a load instruction. And bearing the clock period is not going to be possible. Okay, not feasible. So what we are trying to do is, then is there any way to improve performance or shortening the clock cycle? Okay, so how we can improve the performance? So that is the main topic of the later part of the chapter 4. Okay, so we will learn about the pipeline. Okay, so we cannot change the clock cycles. So instead of that, we are applying the pipeline to improve the performance. Okay, so then let's look at what is pipeline. Let's look at the pipelining analogy. So let's think about the laundry system. So like this. So laundry system can be divided into the 4 steps. First, what is you are doing the washing, right? So washing machine is washing, and then drying, and then what's next? So after the drying machine is drying all the clothes, then we have to fold, right? So we have to fold it manually, and then you have to put your clothes into your drawer, right? So put it in your drawer. Okay, so maybe we can divide each work into 4 steps. Okay. So then now let's think about we have 4 machines. Okay, washing machine, drying machine, folding machine, and putting the clothes into the drawer machine. Okay, so we have 4 machines, and let's think about each step takes 30 minutes. Okay, so 30 minutes. We have 4 clothes. So 4 different persons are doing this laundry. Okay, so then how long does it take to finish the laundry of these 4 types of clothes? So what's the total time? So for each cloth, how long does it take? Yeah. So for each one, just 1 cloth, it takes 2 hours, right? 2 hours. So it is doing 2 hours, and then finishing, we are doing another 2 hours, 2 hours, and 2 hours. So total 8 hours. Okay. However, you know that if we have 4 machines, like washing, drying, folding, and putting the clothes into the drawer. So in that case, what we can do? We can apply pipeline. So pipelining means that, so first, for the first clause, we are doing the washing, okay? And after 30 minutes later, what we can do? So first one is moving to the drying stage, okay? So we are moving to the drying. And then at that same time, what we can do? We can start washing for the next clause, okay? So this is clause 1, clause 2, clause 3, clause 4. And 30 minutes later, the first clause is going to the folding stage. And second one is going to the drying machine. And third one is going to the washing machine. And after 30 minutes later, first one is going to the footing machine. Second one is going to the folding machine. Third one is going to the drying machine. And fourth clause is going to the washing machine. Okay. So this kind of structure is called pipeline. So if we are learning using this pipelining, then what is total time to complete the laundry of these 4 clauses? So here, in this case, yes, we need, okay, so we need here 2 hours and additionally 1.5 hours. So total time is 3.5 hours. So originally it was 8 hours. Now is reduced to the 3.5 hours. Okay. So this kind of structure is called pipeline. If we are laundering like 1,000 clothes, then what is total time? Thousand clothes. What's the total time? So if we are ignoring the last part, if we are ignoring this part, then how long does it take? Every 30 minutes, new clothes is coming into the machine, right? So every 30 minutes, we can start the laundry. Okay, so 1,000 times 0.5 hours. Okay, and after we are doing that, so for the last one, we need another 1.5 hours. Right, 1.5 hours always we need. So total time is 501.5 hours. Okay. So in general and clothes, then total time is 0.5 times n plus 1.5. That's total time, right? So if we are applying the pipeline. And if we are not using the pipelining, then what's total time? Yeah. If there is n clause, then it will be 2 times n, right? Okay. So if n is increasing, then what this value is almost right? So if n is increasing, then it's closing to the 4, okay? So which means that if we are dividing one work into the several stages, then we can increase the performance by that time. So for instance, if we are 4-stage pipelining, then performance is improved by 4 times. If it's a 5-stage pipelining, then performance is improved by 5 times. 10-stage pipelining, 10 times. X-stage pipelining, then X times. So if we are increasing number of stages in the pipelining, then we can improve the performance proportionally. So that's the basic idea for the pipelining. Okay, so we are applying this pipelining concept to the processor to improve the performance. But actually there is some difficulty. Okay, so we will learn about the difficulty, which is called hazard, pipeline hazard. So for instance, 4-stage pipelining should be improving the performance by 4 times. 5 stages should be 5 times, right? But due to some hazard, the performance improvement is not reaching to the 5 times actually. So there is some difficulties, or there is some obstacles to degrade the performance if we are applying the pipeline. So we'll learn about that. Okay, so this concept is pipelining then. Okay, so let's look at this design of the processor, MIPS processor. So in this case, how many stages do you want to break? How many stages you want to apply for the pipeline? It's totally depending on your decision, okay? So you can apply the 2-stage or 3-stage, 4, 5, 6, any stage is okay, but in this figure, how many stages you want to use? What is natural? How many stages? Okay, so here I'm drawing the 5 stage, right? 5 work. Okay, so each stage is working. So let's design the 5-stage pipeline. Okay, for MIPS. Actually, the number of pipelining is totally depending on the designer, hardware designer. Maybe you can break down like a memory into the 2-stage, or instruction decode into the 2-stage, instruction decode and register read should be separated, or ALU operation can be divided into several stages, totally depending on your decision. But anyway, well, let's try to make a 5-stage pipeline. So 5-stage pipelining, we will use 5 stage. So instruction fetch, instruction decode, execution, data memory access, and write back to the register. Okay. So you have to remember. So I think you are already familiar with this stage, right? Because when we are designing the processor, we are designing the instruction fetch part and instruction decode part, actually, which is also including the register read. Why? The reason is instruction decode. Instruction decode is very simple, right? It's just wire connection in our case, right? Do you remember the instruction decode? So 32-bit is coming in, then what we are doing? We are using splitter. Splitter is just splitting the connection, right? That's all. It's very simple. Actually, it's not requiring any AND or gate. This is so fast. So it is too much writer. So at this moment, what we can do is also we can do the register read, because reading the register doesn't take so much time. it is also fast. So we are grouping of these two things into the instruction decode stage because it's so fast. Instruction fetch case, what we can do is we have to read long, right? Memory read. So memory read is a little bit slower than register read. Okay, so we are giving this one. ALU operation, maybe we can give another stage. And data memory, RAM, it is actually slow. And write back, which is writing the register. Actually, that is much faster than the data memory access. But anyway, we are giving the another stage for this write back also. Okay, so you have to remember this 5-stage pipeline. Okay, so let's look at the pipelining performance. As I mentioned, each stage actually has different execution time. Okay, so instruction fetch, which is reading the ROM, it takes like a 200 picosecond. Picosecond, 1000 picosecond is 1 nanosecond. Okay. So 0.2 nanosecond. And register read is very easy. It's fast. Okay, so instruction decode it takes only 100 picosecond. ALU operation is 200. Memory access 200. Register write also 100. So then what's the total time for this load instruction? So we are adding everything. So it's 8 picosecond, 800 picosecond. Okay, so if we are not applying the pipelining, then load instruction case, it takes 800 picosecond. So no pipeline. Store instruction case, insert fetch, read to read, ALU, memory access, but we don't need to update register. So it takes 700 picosecond. All format ALU operation, 200 register read, ALU operation, and memory access is required. Only we need register update. So 600 picosecond. Branch case, insert fetch, register read, and then in the ALU operation, it is comparing and also it is updating the PC value. Actually, at the next cycle, 200. So 500 picosecond. Okay, so if we are using the no pipelining, in that case, what is clock cycle? So every instruction has different clock cycles, right? But we have to fix the clock cycles. So which one do we have to use? The longest one, which is 800. So no pipelining case, one instruction requires 800 picosecond, which means that one clock cycle is 800 picosecond. Okay. Every clock we are executing one instruction. Okay. Okay, so let's draw the pipelining. Okay. So here, if no pipeline is applied, then for each load instruction case, so it takes 800. So this is one clock cycle, and then next one is also 800 and 800. Okay, so this much we need. So for 3 load instruction, we need 2.4 nanosecond to complete these 3 instructions. If we apply the pipelining, then what we have to do? So pipeline case, this single one is one stage, okay? So some stage takes 200 picosecond, some stage takes only 100 picosecond. Which one do you have to choose? We have to choose longest one. Okay, so clock cycle is now 200 picosecond. So after 200 picosecond, then we can finish the instruction fetch. So that work is going to the register read. Okay, so let's look at here. First load instruction case, we are doing the instruction fetch. Okay, and then that one is going to the next stage, instruction decode stage. And during that time, the next one is also executed. So pipelining case, everything should be synchronized, right? So well aligned. So it is aligned. And third is, stage, the first one is going to the ALU stage, second one is going to the register, and third row is going to the instruction fetch. So every 200 clock cycle, new stage. So next stage is moved. Okay, then we can think that this is one stage, another stage, another, and this is another stage. So each one takes 1,000. So 1 nanosecond. To complete one instruction, we have to pay 1 nanosecond, but for the 3 instruction, to complete these 3 instruction, we just (1.4 nanosecond). Okay, so much faster. So reducing the clock cycle of the one instruction or reducing the latency of one instruction is not important, because our goal is that we have to improve the performance of a program, single application. Okay, so single application is including many instructions. Okay. So this is pipelining. So in the pipelining, we can reduce the clock cycle to the one stage only. So for each stage, some stage takes 100 or 200, then we can choose the longest one, 200. Okay, so speed up. If all stages are balanced, so all stages are equivalent, then, so which means that all phase takes the same time, then the improvement is just proportional to the number of stages. Okay, so if we are using the 4 stage, then the performance will be improved 4 times, because this is one instruction. Okay, so one instruction takes this much time. If we are dividing this one into the 2 stages, then every clock cycle, 2 instructions are executed. If we are dividing into the 4 stage, then we can execute another one. So at a single time, then we can see that all stages are running, right? So 4 instructions are actually executed together. So the pipeline speedup is just proportional to the number of stages. Then maybe you just simply think that, okay, so I'm making the 100th pipeline stage or 1,000 stage. Then you can improve the performance by 1,000 times. But this is not actually possible. So MIPS architecture, when we are designing the MIPS architecture, it is designed for the pipelining. Okay, so it is designed to implement pipelining easy. Okay, so for the pipelining, every stage should be equivalent, right? So then it's giving the high performance. So instruction fetch, and then there's instruction decode. If instruction decode takes so long time, then pipelining cannot be applied well, right? So the MIPS architecture case, the instruction decode is also very optimized to reduce the clock cycle. So, and also each instruction should be equivalent, right? So some instruction takes a much longer time, another one takes a short time, then it's not easy to apply the pipelining. So every instruction looks like equivalent. So all instructions are 32-bit. The size are equal, and also task is very similar. Okay, so one instruction doesn't do much work. So everything is 32-bit. That means fetch is easy because every cycle we just need to 32-bit read. And decode is also easy because the format is very regular. So maybe when we are learning about the MIPS architecture, so definitely every instruction should be equal, right? We are just thinking about that, but actually x86, like Intel processor, is not. Intel processor case instruction size are vary. Some instruction is just 1 byte. Okay, so a simple instruction, which is very simple, like a push instruction. Push instruction is just pushing the register value into the stack. Okay, stack means stay inside the processor. Whereas some instruction is much longer. So Intel processor case, there is a four instruction. 4 instruction is loop instruction. So it is initializing the variable and checking the loop and also increasing the loop variable. All of them is performed by single instruction. So in that instruction case, the size is much longer, and also execution time, it takes a lot of cycles. So x86 case instruction is not uniform. Okay, it's heterogeneous. MIPS case, to apply the pipelining, every instruction is 32-bit, and also everything is regular. Okay, just add, and, or. It doesn't have any like a for. For is not instruction in the MIPS. And number of instruction is also limited. So x86 case, Intel processor case, number of instructions is like 1,000 instructions. MIPS case is like 250, but the reason of 250 is that there is an add instruction, add I, add signed, add unsigned. So these are instructions. Everything is different. So even though it's 250, but actually if we are counting the instruction, it doesn't so many. And addressing, memory access. MIPS case, there is only 2 instructions: load instruction and store instruction. Right? Only load instruction and store instruction can load data from the memory, store data to the memory. Okay. Intel process case, add instruction, some add instruction case, it is loading register, and also memory, and also memory to the memory. So pointer operation. So for this case, in the Intel case, to execute the add instruction, it has to access memory 3 times, for instance. For instance, another instruction case, it just read data from the register. In some register, some instruction case, it takes several times to execute that instruction. So it's not regular. Okay, but the MIPS case, only this load and store instruction can access memory. And the memory access is aligned. Okay, so if not, it's not aligned, then, for instance, here this is memory. The address should be like a multiple of 4. Then it is giving the 32-bit. If you are giving like a, it's not multiple of 4, actually this is not allowed in the MIPS, okay? So this is not gonna be possible in the MIPS, but in some architecture, this is allowed. In that case, what this is doing is, this is not allowed, right? Then it is reading 4 byte and another 4 byte, and then it is copying of this 3 byte and this 1 byte and making 4 byte. It's coming up. Okay, even though address is not aligned, some processor is supporting this instruction, this structure. In that case, the memory access is irregular, right? For some address, it takes more time than another one. So MIPS case, to everything regular. Because everything is regular, then applying the pipeline is much easier. Okay, so everything is regular and simple, and so this architecture is called RISC, reduced instruction set architecture. Set computer. So RISC is actually invented to utilize this pipelining. Because of this pipelining, RISC can provide higher performance than the x86. x86 is a CISC, complex instruction set architecture. Okay. So x86 is a CISC. C is complex. So each instruction is heterogeneous. It's different. Then applying the pipelining is not easy. Okay. So then maybe you are wondering that then x86 is not using the pipelining. Do you think x86 is using the pipelining or is not using the pipelining? What do you think about it? Is x86 using a pipelining or not? What is your guess? So you know that using the pipelining can give the higher performance, right? Yeah. So definitely x86 is also using the pipeline. How? You know that x86 has different instructions, right? So each instructions are different. Some instructions are short and some instructions are very long, right? So x86 case, Intel processor, Intel and AMD, what they are doing is instruction fetch. Actually, instruction fetch is also takes different time. So instruction fetch, it is fetching a lot of byte, and then instruction decode is very complicated in the x86. So one instruction, sometimes one instruction is very small, and some instruction doing a lot of complex work, right? So like a for loop, for instruction. Then x86 case, this instruction decode is generating the micro operation. Micro operation. So for instance, just simple add case, micro operation is just add. For instruction, it has to many things. Then for instruction case, it is generating the first is initialize, and then check, and then increasing, and then something jump. So these are generated, okay? So one instruction is coming into this instruction decode, then many micro operations are generated. And then here, later part, they are using the RISC, because each micro operation looks like a simple instruction. Okay, so these are the simple instruction. So x86 case, this insertion decode is very complicated, complex. After analyzing the instruction, then later part, the normal RISC that we are learning, like MIPS architecture, is actually used for later part. So that's the reason why x86 is, maybe you know that there is some comparison between x86 and like Apple M1, right? So Apple M1 is ARM processor, and x86 is Intel processor. So when we are comparing which is more generating, which is hotter, which one is generating the more heat. Intel is generating more heat. So high energy consumption. Okay. The reason is because of this insertion decoder part. It is very complicated. So Apple M1 case, the input is actually, it's like a micro operation. Okay, because instruction looks like a micro operation. Intel processor case, it has another stage, which is decoding part. Because of this decoding, it is consuming a lot of power. Because of that, it's very hot. Okay, so modern RISC processor case, it is removing this front part. Because of removing this front part, it can accelerate the performance and reduce the energy consumption. Okay. Okay. So now what we are learning about that is we are learning about the hazard. So we are learning about the pipelining hazard. So what's the meaning of a hazard? It's like a danger, right? Hazards mean danger or difficulty, danger, difficulty. So the pipeline hazard means there is some situation that prevent the starting the next instruction in the next cycle, which means that it is preventing the pipelining. So in the pipelining, every clock cycle, what should be? So this is stage. Next cycle, next instructions to be executed, right? Every cycle, new instruction should be executed. So every cycle, new instruction should be executed. But because of some reason, we cannot execute next instruction. So then what do we have to do? We have to wait, right? We have to wait one clock. Okay, so that is called hazard. So we'll learn about the 3 types of hazard. So this is called bubble. Okay, so we have to add bubble. So in this bubble, we are not executing anything. So it's just empty. No instruction is executed. Or we are saying that this is pipelining stall. Okay. So there are 3 types of hazard. First one is structure hazard. Second one is data hazard. And third one is control hazard. Okay. So do you guess which is most difficult to resolve? Even we didn't know about what is hazard, right? So definitely this is easy, right? And this is, last one is most difficult to solve. Okay. So let's look at what is it? Structure hazard and data hazard and control hazard. Structure. The meaning of structure means it is related to the hardware. Okay. So required resource is busy. So let's look at structure hazard. So conflict, use of the resource. We have to pay the bubble. So let's think about it. We have instruction fetch, instruction decode, execution, memory, and write. Okay, so this is five-stage pipeline. Instruction fetch is access the memory, right? Instruction memory. Memory stage also access the memory, data memory, right? So currently we are separating the instruction memory and data memory, but let's think about that. There is no separation. Okay, so we have only single memory. Okay, only single memory. So we just have a memory. So insertion page is also reading memory. Data memory, mem stage also reading the memory. Okay, insertion patch, insertion patch. So let's think about it. The first one is like a load instruction. This one is like add instruction. Okay, load instruction case. What is load instruction 3? It is reading data from the memory, right? But instruction fetch is also reading instruction from the same memory. So there is only single memory. Then we cannot read data twice at one cycle. Okay, so this cannot be executed because of memory access. So we have to put bubble here. Okay, so add instruction can be starting at the next instruction. Okay. So here, what this bubble is happening because of memory, which is resource. This resource is conflict. So two different stages, like a memory stage and instruction fetch stage, are trying to access the same resource, hardware resource, right? Hardware resource. So that means we have to block one of them. Okay. So that case is called structure hazard. So like a load store instruction case, we need data access, but instruction fetch is also need memory access. Then instruction fetch should be store, so wait for the next cycle. Okay, so it is choosing the bubble. Okay, so this is a structure hazard. Then how can you solve this problem? How can you remove this structure hazard? How can you do that? Structure hazard is very easy to solve. So for instance, you have in your home, you have one car, okay? but there are two people, they want to use the car at the same time. So it's a conflict, right? Okay, there is a single car, but there are two persons, they want to use the car at the same time. So that means one of them should be wait until one person is finishing the use of this car. So because of that, there is conflict. So we have to wait. How can you resolve that problem? In this case, the easiest way is that you are buying another car. Right? So if there are two cars, then there is no problem, right? So structured case is very easy because you are just putting more resource. So you are just adding additional hardware, then you can easily solve it. Okay, so this loads memory and instruction fetch case, because of there is a single memory, there is a conflict. So to avoid this one, what we have to do is we have to prepare another memory for the instruction fetch. Okay, so instruction fetch, we are using instruction memory. And for the date, we are using the data memory. So resources are separated. So another hardware is provided, then we can solve this structure hazard. Okay, so solving the structures is very easy. Just putting more hardware, just paying more money, then it is solved. Okay. Okay, so next time we are looking at another hazard, which is data hazard. Data hazard can be also solvable a little bit. And then the last one is control hazard. That's most difficult. Okay. So we are in the 5-stage pipelining. 5-stage pipelining case, hazard is just a single or two bubbles. But if we are dividing more stage, like 100 was 10 stage, then this hazard becomes more important. Okay, so we'll look at what is this data hazard and control hazard, and how to solve this hazard part. Okay. Okay, so any question? Let me announce again. Next Monday, you have to finish the design of the MIPS processor. Okay. And also, I will give you another homework for this design of the processor, like implementing another instruction. So currently, you are not implementing jump and link or jump register, right? So current one, it doesn't support jump and link, jump or register. But after you're implementing this instruction, then maybe you can support Fibonacci sequence, right? So that will be the final project. Okay. So anyway, on Monday, what you have to do is you have to implement like a branch equal, load, store, add I, jump. So this part should be supported. Okay. Okay, no question? Okay, so bye.